introduction, and good morning, everyone. My lecture presentation for today deals with Lissajous frequency modulated MEMS gyroscopes and a way we have devised to reduce the generation of spurious harmonics that occurs during the operation of these devices. Let me first spend a couple of words on the main gyroscope architectures that are popular nowadays. As I guess you know, gyroscopes are based on mechanical structures with two resonant modes that can be either degenerate or non-degenerate. We usually call these mode matched and mode split architectures. So the mainstream gyroscope architecture nowadays is based on amplitude modulation, where you have a drive mode that is kept in oscillation at a controlled velocity by means of an external oscillator, and a sense mode that is instead sensitive to the Coriolis force. We have seen in the previous lecture the AM mode split architectures, which are nowadays the best performing ones. And I would also cite the AM mode matched ones, which are a bit less common, but they're performing as well. And they are usually operated in force to rebalance. That is, the sense frame is not left free to move under the effect of the Coriolis force. Instead, it is kept still in its rest position by a force feedback loop that counteracts the Coriolis force. The other main gyroscope architecture is based on frequency modulation, where you don't have a distinction between a drive and sense mode. Instead, both modes are kept in oscillation, and the effect of an external Coriolis force is to modulate the resonance frequencies, hence the name frequency modulation. Again, they can be based on mode matched and mode split structures, and the latter ones are the so-called Lissajous FM gyroscopes, which are the topic for this work. The main advantages of these architectures being the wide full-scale range they can achieve, and at least theoretically, the high stability and repeatability of the scale factor that they should be able to achieve. So I will summarize here the working principle for Lissajous FM gyroscopes. As I was saying, they are based on mechanical structures that are mode splits. So we have the two resonant modes that are usually split apart by hundreds of hertz. And if you make both modes oscillate, you see how the math describes a Lissajous pattern, and hence the name Lissajous. The frequency modulation effect is instead readily understood from the equations. This is the equation of motion for the X mode, written in phasor form. You can recognize in red the inertial term and the elastic force. The damping term is 90 degrees apart as a phasor, and it is usually compensated in operation by an external electrostatic force Fx, which is generated by an oscillator loop, so we can neglect those terms in the calculations. The only remaining term is the Coriolis force, which is proportional to the velocity on the y-axis, and therefore it is represented by a phasor that rotates with respect to the x ones. As you can see in this rotation, it modulates the resonance frequency of the x-axis, since the sum of the three terms has to be 0. And this is how you get a frequency modulation effect. Of course, the same happens for the y-axis. And if you're able to read the frequencies of the resonance frequencies of the two axes and sum them, you can see how you get a frequency modulation effect, where the external angular rate, omega z, is weighted by a ratiometric scale factor, alpha, which is in principle only dependent on the modal shape of the two resonant modes. You can also see here a sinusoidal modulating term, which is often referred to as continuous time reversal of the scale factor. This is basically an amplitude modulation that is superimposed to the frequency modulation and allows you to shift the signal away from the slow thermal drifts of the resonance frequencies. So in the next few slides, I will be describing the issue of the generation of spurious harmonics that we observe in these devices, and we will see a way that we have devised to try to attenuate this issue. So during the operation of the device, as you can see from this graph, the MEMS undergoes instance of full frequency modulation when the trajectory is circular, and instance of full amplitude modulation when the trajectory is linear. This AM effect is undesired, since it generates a distortion of the Lissajous pattern, as you can see here in the right figure. And in turn, it can be seen in the output spectrum as the generation of spurious harmonics at multiples of the frequency split of the two modes. Of course, this is a problem because it limits both bandwidth and stability of the sensor, since you will have to low-pass filter these harmonics. And the main reasons for the generation of harmonics are two. The first one being that it is difficult to design a control loop for the amplitude of the oscillations that is effective at the frequency split of the two modes. The other one being the electromechanical modal coupling between the modes, which is the issue we try to tackle in this work, and it is particularly relevant at large displacements. So we had this idea to redesign the sensor by allowing a lower motion amplitude, since the scale factor is in principle independent on the motion amplitude, while the modal coupling is. So if you reduce the motion amplitude, you should in principle attenuate the modal coupling while keeping the same scale factor. The issue is that reducing the amplitude of the displacement XA also increases the output noise. So the idea was to compensate for this higher noise by redesigning the structure by increasing the electromechanical transduction factor, this X, to compensate for this higher noise. So we took a structure from a previous work called mass gyroscope. We redesigned it with a larger area, 2 by 2 millimeters, which allowed us to achieve a higher transaction factor by redesign of the electrodes, and also a better modal decoupling, since by means of a smart redesign of the suspension elements of the structure. So in the next slides, we will see the experimental results of this low motion amplitude operation. In order to characterize the sensor, we have coupled the MEMS device to an ASIC, which implements a couple of integrated oscillators for the X and Y axis. As I was saying, the output for this sensor is a frequency which we extracted directly from the oscillator loops. This is a typical output spectrum where you can see that the signal is modulated around the frequency split of the two modes, which was 330 Hertz for this work. You can see a big peak, central peak, which is the DC quadrature, which was left uncompensated in this work. And the two side peaks are the signal that we applied at 5 Hertz. So basically, you will have to demodulate this signal to reconstruct the input rate. Okay. We made the oscillator loops based on charge amplifier front ends with selectable feedback capacitances. This was needed to change the amplitude of the oscillations in operation. This is made possible by the fact that the output voltage, the amplitude of the output voltage at the charge amplifiers is controlled by an AGC control loop. So as you can see from this equation, if you change the feedback capacitances, that is the gain of the charge amplifiers, you get a reduction by the same factor in the amplitude of the displacement. These are the output spectrums that we have measured. As you can see, again, we have a DC quadrature peak at the frequency split at delta and a huge second harmonic. We have demonstrated that by reducing the amplitude of the displacement, the second harmonic reduces while the first one stays basically unchanged. What also remains unchanged is the output noise. As you can see, it's basically below 10 millidps per square root of hertz in bandwidth. And this was due to the fact that the charge amplifier, when you change its gain, does not become the dominant noise source in the system. So noise is limited by other sources in the readout chain. And that is how we achieved a 51-fold reduction in the harmonic distortion of the sensor. So to conclude, a brief recap of what we did, we have noticed that the generation of spurious harmonics is a big issue. Is a big issue for the operation of LFM gyroscopes. And however, you can attenuate at least partly the generation by reducing the electromechanical modal coupling between the modes. We achieved this by recurring to a low motion amplitude operation, and we had to redesign the sensor to have a larger area to compensate for the higher noise. And in the end, we demonstrated that we achieved a 51-fold reduction of the harmonic distortion by, however, keeping the noise constant, let's say below 10 millidps per square root of hertz. So the next steps for the system characterization include, hopefully, the characterization in terms of full-scale range, bandwidth, and temperature stability. And if you want more details, this work has already been published as a sensors letter, so you can go check that out. And I'll be glad to answer questions if you have. Thank you.